In our last lecture, we have discussed the theory of simple linear regression. In simple linear regression, we have one independent variable x, one dependent variable y, and we connect them through a linear relationship, that is w0 plus w1x. We have discussed how to find this w0 and w1. At the end, we have seen that given a particular dataset xi, yi, we should be able to fit a straight line between this dataset. Will fit a straight line or not? We have taken that decision initially looking at the dataset. And after we fit, it may look that my fit is good. It is showing the trend that is there in the raw dataset. But then there must be some way I can quantify how good my fit is, and that is what we are going to discuss in this lecture. First, recall what we were discussing previously. We had a data set that is given by xi, yi, I equals 1 to n. First, let's start by recalling what we were discussing in last lecture. We have a data set xi, yi for I equals 1 to n. Through this dataset T, we want to fit a least square regression y hat equals w0 plus w1x. In this dataset, every data is an ordered pair, so x1 is connected to y1, x2 is connected to y2, etc. To get this w0 and w1, the regression coefficients, we minimize the cost function e, which is a function of w0 and w1, which is given by 1 by n into yi minus y hat I whole square. Yi is coming from experiments and y hat I is our estimate from regression model. Now we have seen that after we do this minimization, we have w1 to be sxy divided by sxx. Sxy is the summation of xi minus x bar into yi minus y bar from 1 to n. Similarly, sxx is the summation of xi minus x bar whole square. Here this x bar, y bar, etc., they are the average of x and y respectively. Once we get the w1, we can find the w0 very easily from y bar minus x bar multiplied by w1. Now we are about to find out that how this least square fit is matching the trend in our data. One way to think about it, that the difference between yi and y hat I, that should give us something. So we have already defined that term as residual. So this ei, which is yi minus y hat I for all I, we can see that what would be the summation of this. That may give us something. To get this, I bring this expression of y hat from here and I plug it in here, y hat I as this w0, w1xi, and then this w0 I replace with this expression of w0 y bar minus x bar w1. Therefore, what I have is yi minus this y bar minus xi minus this x bar w1. So if I now sum this ei from I equals 1 to n, what we will get is sum of this yi minus y bar and this w1 multiplied by xy minus x bar. So let us check this yi minus y bar, sum of that. If I break this sum, it would be summation of yi minus summation of y bar. Now summation of yi, from here we can see that this should be n into y bar, and then in the second term the y bar can come out of the summation sign. That means this should be only summation of 1. So that gives us again n. Therefore, it is ny bar minus ny bar, and that is 0. And similarly, we should be able to show that summation of xi minus x bar equals 0. So here this xi minus x bar and y minus y bar, together we can write that it is 0. Thus the summation of ei is always 0 in our simple linear regression, and it doesn't give us anything. Rather, it should be prudent to think about that square of them, summation of that will give us something, because anyway that is something related to the cost function. Average of that is the cost function. So let us look at the square then. Let's start with this yi minus y bar. And why I am taking this quantity, it will be clear very soon. I can write this as yi minus y hat I, and then y hat I minus y bar. And then what I am going to do is that I will square both sides. So if I square both sides, I have this yi minus y bar whole square. And here I have yi minus y bar whole square. And here I have yi minus y hat I whole square. So this is actually, this term is indicative of our error that we are looking for. This is indicative of the residual, this yi minus y hat I. And so this is the square of that residual. But then again, there is this cross term 2 times y hat minus y bar, y minus y hat. So let us do something about this cross term first. So let's look at this cross term y hat minus y bar, y minus y hat, and let's recall this w naught is y bar minus x bar w1, and y hat is w naught plus w1 x. Therefore, I can write here this, replace this w naught with this one, that y bar plus x minus x bar w1. So I have removed w naught and brought w1 in place of that. So now this, look at this y hat minus y bar. So I can get the y hat minus y bar from here. That is x minus x bar into w1. Then the second term is y minus y hat. So expression of y hat is this one. And then y minus y hat therefore will give me y minus y bar minus x bar into w1. So let's write that this is xi minus x bar w1, and then within third bracket we have yi minus y bar minus xi minus x bar w1. Now if we multiply this, it will give me xi minus x bar multiplied by yi minus y bar minus xi minus x bar whole square w1, and there is w1, one w1 is here, that is outside. Now this term must be looking familiar, because we know that the summation of this term over 1 to n is sxy, and the summation of this term xi minus x bar whole square, that is the sxx. Now we take summation both sides. So here I take summation and here I take summation. So it gives me summation of this cross term here is yi minus y bar minus y minus y hat is equal to summation here, and summation of this is sxy, summation of this is sxx into w1. Now you see this sxx into w1, that is sxy. So sxy minus sxy is 0. So this term gives 0. So now if I see this one, this expression here, I can now see that summing up both sides, because sum of this cross term is 0, I can clearly say sum of this yi minus y bar whole square is equal to sum of y hat minus y bar whole square plus yi minus y hat. This is the part we are interested about, this is the residual, is square. So I term this 3 summation, I take that as sum of square. This is sum of square total. So this tells us the average value of y minus the value of y at any given point, their difference, squaring it up. And then here average value of y and minus the estimation of y, their difference, we square it up. If these two are equal, SST and SSR, then we will assume that, well, this estimation y hat and the actual experimental value yi, they are probably same. But in reality, they are not same. That is why this third term is coming. This is sum of square residual. Residual is making the difference between experiment and the estimation. So my residual is yi minus y hat whole square. That is what we call sum of residual. Now we see that this SST as SSR plus SS race. This is my SST, SSR and SS race. And this SSR, which is the regression part, sum of square regression, y hat minus y bar whole square, I can rewrite as this y hat minus y bar as x minus x bar w1. We have already shown this. You can see it from here. Y hat minus y bar. If I use this 2, I'll get it x minus x bar w1. I square it up and it gives me sxx w1 square, because sxx is xi minus x bar whole square summation. Now I define my first term, which will give me something about the quality of regression, and that is something extremely important. If you use one quantity to check the quality of regression, this should be it. That is what we call coefficient of determination, and it is indicated at r square, and this r square is SSR divided by SST. So this is my SSR, that is the sum of square regression divided by SST, sum of square total. Of course, the total will be probably more than the regression, or at least equal to the regression. So this term is likely to be less than 1. And this is what it is. This should be 1 minus SS race by SST, because this SS race and SSR, that makes SST. And you see that all of them are square here, so they can't be negative. Therefore, this particular term here, it can be 0 or some positive number less than 1. Therefore, r square will remain between 0 to 1. Now, r square is again SSR by SST, which we write this SXY into W1 by SYY, because this SST is our SYY and SSR is SXY multiplied by W1, that we have shown already. So now this W1 is SXY by SXX. If I write then it becomes SXY whole square SXX SXY. And this quantity is between 0 and 1, which means that if I take a square root here, that will remain within -1 to +1. Now if you see it here, this root over SXX SXY, it should be always a positive number, because there is no way SXX or SXY could be negative. They are sum of squares, so that is always positive. Therefore, this particular term is going between -1 to +1, indicates that SXY could be positive or negative. And there are implications of SXY being positive or negative. We will see it quickly. This particular term is, of course, if this is r square is r squared, then this is r, and this R is called correlation coefficient, that is Sxy root over Sxx Syy. Both these terms are very important terms, R square and R, and they give us a lot of information about the quality of regression. There are also other terms which tells us about the quality of regression, but we will just stick to these two for now. So let us see the implication and significance of these two. First of all, this R square, it shows that 1 minus SS raised by SST. So if R square is 1, what does that mean, or very close to 1? It means that this SS raised is very small. SS raised is small means the residual is small. The square of residual, if I take the sum, that is small, which means my regression line is actually passing very, very close to the actual data point, because this yi is my estimation, yi is actual experiment. When they are very close, then this term will be very small and R square will lead to 1. So it says that whatever the SST that is captured very good by SSR, which means that the variation is y that is given in the actual data, which is given by the SST, is captured by the regression line very well. On the other hand, if it goes other way around, one extreme is 1, then other extreme is 0, and in that case, if it is 0, then we have to understand that SS race is giving us everything. SS race is equal to SST and SSR is basically 0, which means it is my regression line is far away from every data point actually. So it is missing all the information actually. It is nowhere close to any data point. So it is missing all information. So it is not a good idea to have R square tends to 0. It tells us that this is not a good regression. Linear regression will not work here. Similarly, if we look at the value of R, then R greater than 0, it means that Sxy must be greater than 0. And what does that mean, Sxy being greater than 0? Now look at this Sxy. It is xi minus x bar, yi minus y bar. Now the regression line actually passes through this xi, yi. If we look at this, y hat is w naught plus w1 x, and here you can see y bar is w naught plus w1 x bar. So that means regression line passes through the x bar y bar point. So now that regression line passes through the x bar y bar point, when I have xi, let us say I have an xi that is greater than this x bar, that is greater than the average. I am here at x bar. If yi, so this is my xi, yi. So when xi is greater than x bar, if yi is also greater than y bar, then this term will be positive, and with lots of positive terms like this, we will have R greater than 0, or Sxy greater than 0 means R greater than 0. So it tells us that we have a positive correlation. When x increases, y increases. This is the information we get from the data. Similarly, when it is the other way around, that means R less than 0, then it tells us that this line should be like this. When xi, let us say at this point xi, yi, when xi is greater than this x bar, yi is actually less than this y bar, that is giving Sxy to be negative, R less than 0, so it's a negative correlation. So it's the line actually goes like this, So it is a decreasing line. It is still a straight line, but it is a decreasing line. So that is why we call it a negative correlation. When one increases, another decreases, as opposed to the positive correlation, when one increases, another also increases. And then the third case, that is when R is equal to 0 or very close to 0. When R is close to 0, it tells us that there is no correlation at all, and Y and X cannot be linearly dependent. We have to find out some other kind of relation between Y and X. Our current theory is not good enough for this data set. Looking at all this, it looks like that, well, R square equals 1 is probably a very good thing. But it may not be always so. When R square is equal to 1, that basically means that this SS race is 0, which means this yi and y hat I, they are matching more or less for all data. Therefore, my regression line is passing through all data. It is probably overfitting. It is probably fitting too much than what is necessary. When a new data will come, it may not fit that. So it lacks the generality of regression. The purpose of regression is not to fit the data exactly, but to bring the big picture that will fit many data and many more data that are not used in creating this regression. That is why R square very close to 1. It may be good in some cases, but not necessarily. We are now ready to summarize the finding. We have seen at least two quantities, R square and R. Both are important quantity to evaluate the quality of regression. R square high is good, close to B1, but too close is not good, and certainly when it is equal to 1 is not good. As your exercise, you think about what kind of dataset can produce an R equal to 0 and discuss in which cases you can have this kind of dataset. So that's all for this lecture. Thank you, and I'll see you in next class.